In this lesson, we are going to find the area between two curves. Finding area on a graph really sounds like we're trying to take an integral of something, the integral of the function that is graphed, right? So the integral of f of x would be, well, we can graph this function, and then we can write out the integral, and then we can find the value of that integral by finding the area between -5 and 0. Okay, let's do this. In order to graph that function, we need some y values and some x values. We know this is a parabola. I know it goes through 0, 4, right? 0, 0, 4. 0, 4 is right here. I'm going to use blue for this whole first function. And for the second function down below, I'm going to switch colors to pink because we're going to be graphing two functions on the same grid. Okay, let's find the min or the max of this function. We know that there's going to be a maximum on this guy because the very first number, that ax squared, a is a negative number, so it's going to be a frown. Or you could think of, if you took the second derivative, that would be a negative number, right? 2 times -1/2 is -1, and then our new exponent of 1 times -1 is -1. So since our second derivative would be negative, our graph would be concave down. The graph of f of x is concave down. So something like this or something like this. If we find the min or the max, we can figure, well, there's going to be a maximum. We can find out where that is, and then we can reflect that point across the axis of symmetry. There's some Algebra 1 stuff. So let's start by finding the min-max. Okay, the min or the max is found where f prime of x equals 0. Our first derivative is -x minus 2. We set that equal to 0. Add x to both sides, we get -2 equals x. Okay, then we plug that in to f of x to find the y value. F of -2 equals, and we can do this math, we get 6. So -2, 6 is the vertex of our parabola. Cool. -2, 6, boom, right there. Here's our axis of symmetry. I'm not going to draw it, but this point is going to reflect across the axis of symmetry and go here. Just so we have some other good points, 2, -2 is a point that is on this. -6, -2. 1, 1.5. It's not a great point, but it's something. -5, 1.5. And then -1, 5.5. -3, 5.5. Okay, you can find most of those points by typing this into y equals and getting a table. Let's go ahead and draw this out. Looks like this. Parabola. Cool. If we wanted to find the value of the integral from -5 to 0, we would draw along the x-axis from -5 to 0. And then we would draw straight up and straight up. And all of this stuff right here, we're going to shade it in. All of that is the area represented by that integral. Cool. All right, now we're going to actually take the integral to find that area because we were told to find the value of that integral. Okay, so the integral from -5 to 0 of f of x dx. F of x is -1/2 x squared minus 2x plus 4 dx. When you take the derivative, your exponents move down and then decrease by 1. When you take an integral, your exponents increase by 1. And then you divide these by your new exponent. minus x squared plus 4x. And then normally there would be a plus c, except we're evaluating at two numbers. X equals -5 to 0. We're going to plug in 0 everywhere. You get 0 for your first whole bracket, minus -1/2 times -5 cubed minus -5 squared plus 4 times -5. Okay, and as of course we all plug that into our calculator, we end up getting 145/6. It doesn't ask for a label, so we don't have to put a label, but it's square units because it's an area. So let's go ahead and put that. Cool. Next part. Graph the function g of x equals 1/2 x plus 4. I'm not going to push this paper down. You can see it on your own, but it's g of x equals 1/2 x plus 4. That is linear. Our y-intercept is 4, and our slope is 1/2. So down 1 and left 2. Down 1, left 2. Down 1, left 2. And so on forever. Use this little guy as a straight line. Fantastic. Okay, so we graph that function on the same grid above and then find the value from -5 to 0 of g of x dx. Integral -5 to 0 of this function, which is 1/2 x plus 4 dx. So that x is going to become x squared, divided by 2 is 1/4, plus 4x, normally plus c, but we evaluate now at -5 and 0. Okay, we'll plug in 0 for the first bracket. We get 0. Plug in -5 to the second bracket. 1/4 times -5 squared plus 4 times -5. Calculator, that is 55/4. And again, square units because we're not given like centimeters or anything like that. Cool. So we found the area of the blue area. So above the x-axis, below the blue curve. That blue curve was f of x. The pink curve is, well, line is g of x. Okay, and then it says, using a different color, shade the region for which this value represents the area. Okay, so again, we're going -5 to 0. And go up until we get to g of x, which is the line. And then we shade in here. You might notice that these two curves, like the blue and the pink, intersect at x equals -5 and at x equals 0. They intersect at those 2 points. I would imagine that's why these numbers were picked. They surely did not come out with really nice numbers for our area answers, but at least the two graphs cross over or intersect at those points. All right, that's interesting. Okay, what do you suppose you would do to find the area of the region that is located in between the graphs of f of x and g of x? That's also called bounded. In between is bounded. So if we wanted to find, I'll trace in black this time, the area here, just that area, it's the blue area that does not count the overlap here. So it's the area that is under the blue but above the pink. So it looks like we can take that blue area and subtract the pink area, right? Whole blue area minus the pink area, and you get just the singly blue. Okay, so to do that, we're going to subtract the areas. Subtract the areas. So the area between equals the blue first. It was 145 over 6 minus 55 over 4. And calculator that up, we get 125 over 12, which is about 10.417, and again, square units. Okay, so you take the whole area, subtract out the piece you don't want, and then you get the piece you need. Sweet. Next. Now we're going to find the value of the definite integral below if f of x equals 1/2 x squared minus 2x plus 4 and g of x is 1/2 x plus 4. So these are the same f and g as we had before. So I'm going to stick with blue for f and pink for g for as long as we need to. Okay, so it is f minus g. We got this integral from -5 to 0 of f minus g dx. Let's plug in the f of x function right here, 1/2 x squared minus 2x plus 4, and g is 1/2 x plus 4. Okay, we can do a little bit of combining like terms instead of taking the integral immediately. Okay, combining like terms. This has x squared, nothing over there does, so 1/2 x squared. Negative 2x minus 1/2 x is negative 2.5 x, so that's minus 5 over 2x. Right, because that's 4 over 2 and 1 over 2. And then we've got 4 minus 4, which is 0, so that disappears, dx. We take our integral, x cubed 1/6 minus x squared 5/4. Normally plus c, but we're evaluating. From x equals -5 to 0. Okay, we talked about plugging in 0 makes our first bracket 0. Plugging in -5 is going to be 1/6 times -5 cubed minus 5/4, -5 squared. Whoops, bracket, not parentheses. Okay, so that's going to reduce. And it is hopefully not a surprise that this reduces to 125 over 12. There we go, 125 over 12 square units. So it looks like if we just subtract the two functions and then take the integral, we end up finding the area that is between our two functions instead of having to do one integral, the other integral, and then subtract. Doesn't that make sense though? Isn't this the same thing as the integral from -5 to 0 of f of x dx minus the integral from -5 to 0 of g of x dx? Didn't we learn that before? We sure did. We did. We learned that. You're allowed to split up two continuous functions, and then you just put that symbol in between, so minus in between, and you got it. It's the same exact stuff. So what do you notice about this value? Oh, I'm sorry, spoiler alert. It's this. Whoops, I got excited and I forgot to look at my notes. So this is the same thing as this, and it's the area between the graphs of f and g. So write whatever you want there. So the integral of f minus g equals the integral of f minus the integral of g. I'm going to put my x's in there. Which equals the area between the curves. Okay, so this brings about the general way that we will find the area between two curves. So we're going to do the area equals the integral from a to b of f of x minus g of x dx, provided that, so it also has to be true that f of g, or as long as f of x is greater than g of x on the interval from a to b. So f has to be greater than g on a to b. F can be equal to g at the endpoints, though. Okay, we just saw that, right? Our endpoints were our points of intersection between our f and g functions. That's why there's no equal signs on here. Cool. So find the area of the shaded region R that is bounded by y equals the sine of pi x and y equals x cubed minus 4x. Okay. So bounded by means from intersection point to intersection point, what's the area between? If you are coloring in your coloring book, what's that area? You might notice that on this graph, we did not find this area. That's because it's not bounded. There's no other like coloring book edges to that shape. So we can't really do anything with it. All right, so we are going from this point right here where x equals 0 to this point over here where x equals 2. So it looks like a equals 0 and b equals 2. There are points of intersection. Between those two functions. All right, sine of x or sine of pi x is the one that goes like up, down, up. So I'm going to put blue for this one again. Y equals sine of pi x. And I'll do pink again for the lower function just to be consistent. This is y equals x cubed minus 4x. Awesome. So the area between our two curves equals the integral. Area equals the integral from a to b, that's 0 to 2, of f of x minus g of x, the top function minus the bottom function. So that's going to be sine of pi x minus x cubed minus 4x dx. Okay, so you might find it easier like looking to actually separate these two little integrals out. I would totally understand that. I'm going to go ahead and do it that way because it's easier to think of sine as its own deal and then this polynomial as its own deal. So I'm going to separate them. So this equals the integral from 0 to 2 of sine of pi x dx. Then the integral from 0 to 2 also, keep the dx. I'm going to distribute this negative, making it negative x cubed and then plus 4x. That way I can put a plus. Is that okay? Okay, distributed the negative to make that into a plus. You can leave it. It doesn't really matter as long as you pick a method and go with it. Okay. The polynomial one is definitely easier to take that integral of. Let's do it. So it's going to be plus a negative x to the 4th. So negative 1/4 x to the 4th. And then plus 2x squared. And all of this is evaluated from x equals 0 to 2. I'm going to keep going. Plus bracket minus bracket for this one. Did I do that step by step? Heck yeah, I did. Okay, so we're going to plug in the 2 here. So this is negative 1/4 times 2 to the 4th plus 2 times 2 squared. And this is going to be 0, right? Plug in 0, you get 0. So this becomes negative 4 plus 8. So it becomes 4, negative 4. All right, no, positive 4. Ooh, mess that up. All right, because this is 4 and this negative 4 and this is positive 8. Negative 4 plus 8 is 4. This is 0, so we don't care about it anymore. All right, over here, sine. Sine is annoying because it is the sine of pi x, not just the sine of x. So this guy is one of those chain rule problems, but we're taking the integral. So we need there to be the derivative of the inside function here, and it's not there. We have a pi x, but we need a number here. Remember, pi is a number, so if this was 3x, we would need a 3 here. To do that, we would multiply by 3 and multiply by 1/3. We need a pi, so we're going to multiply by pi, and we're going to multiply times 1/pi. And that's going to fix our problem. Okay, the 1/pi is going to trickle down. And we will take the integral of sine of pi, well, pi times sine of pi x. Integral of sine is negative cosine. And then we keep the inside safe. And we are going to evaluate this from x equals 0 to 2. Gosh, this problem was a lot longer than I remember. Okay, so the 1/pi is really multiplied times this negative cosine business. Okay, bracket this up. 1/pi times our first bracket minus 1/pi times our second bracket, because the 1/pi is multiplied times this whole thing, so it gets distributed to both pieces. So this is negative cosine of 2pi, and this is negative cosine of 0. Cosine of 0 is 1, so this is 1 times 1/pi, which is 1/pi. Negative times negative is positive, so plus 1/pi. Over here, cosine of 2pi is 1, and then there's a negative in front of it, so it's negative 1. Negative 1 times 1/pi is negative 1/pi. Oh my goodness. And then we are going to combine like terms. Negative 1/pi plus 1/pi is 0. So all that combines to get 4. Oh my gosh, why did we do that difficult of a problem for the first one? What the heck? Normally it's going to be a little bit prettier than that. Hopefully you can do some like combine like terms or something and then just take your integral and you don't have to split it up. But this does work. Cool. Next page. Pictured to the right is the graph of f of x equals this polynomial. You might be like, oh my gosh, there's so many fractions. But those fractions actually make us a little bit happy. Because when we take our integral, aren't they all just going to disappear? No, they won't. They become worse. Oh my goodness. Oh, we're allowed to use a calculator on this one. Sweet. So picture to the right is this, which is definitely the curve because it's got that cosine and it's a polynomial. That's really messy. And then L is tangent to f of x at the point 0, 3. That means that this line and this curve both touch 0, 3. They equal each other at 0, 3. Interesting. And the slope of this equals that, the slope of that, f prime of x equals the slope of that line. f prime of this, f prime of 0 equals the slope of that line. All right, find the area of the region R. R is over here. There is not much to that. There is only one function, and it's the curvy guy, the cosine guy. We want to find the area between this spot and this spot. So we're looking for R is this region. So we need to figure out A and B. B is not so hard to find. B is 0, because that's where that little area gets cut off. B equals 0. But A equals what? Okay. Well, this is the spot where that curve touches y equals 0. So if we plug in 0 here for f of x, we want to know where does this all equal 0. And how did I find that before? Set 0 equal to all of this stuff. Oh my gosh, I just literally plugged this into y1 and then I found the zeros. Do you have a calculator with me? I'll use this. Clear all that out. All right, we're gonna do the x cubed over 4. You guys see that? Kind of. Alpha y equals gets me a fraction, so we got x cubed over 4 minus alpha y equals, oh, gross, to the right, minus alpha y equals, enter, x squared over 3 minus 0.5x. Right, 1/2 x is 0.5x, and then plus 3 cosine of x. Am I in radians mode? Yes. Okay, so I've got my y1 plugged in, and I'm going to go to second and then trace to get to that calc menu, and I'm going to hit number 2 for a 0. That's literally all I'm looking at. We're looking for this 0 over here. So we're gonna start, I've never done it on this calculator before. Oh, I just like trace. Okay, that's my left bound and my right bound. And then the 0 is at negative 0.9. I don't know. I've never done this before. Oh, there it is. There it is up there. Negative 1.373. I've only ever done this on the actual calculator. Negative 1.373. I found a 0 using a graphing calculator. Cool. So we've got A, we've got B, we've got f of x, which is this guy. So we literally just need to find that area. It is not pretty working it out by hand. We're going to do this one in the calculator. So we're going from negative 1.373 to 0 of y1, which is f of x dx. You cannot see what I'm writing. There we go. And the calculator gives you 2.903. And this equals the area of region R. That's it. That's what you were asked to find. This is stuff we did in the previous unit, except we've never found like the A value. We've always just been told what A and B are. All right, great. Next one, find the equation of line L if it is tangent to the graph of f of x at 0, 3. Okay, we talked about this for a second. If L is tangent to the graph of f of x at 0, 3, that means the slope of L is f prime of that x value, 0. So f prime of x equals 3/4 x squared minus 2/3 x plus minus, Mrs. Campbell, minus 1 over 2. And then derivative of cosine is negative sine. So minus 3 sine of x. Goodness gracious. Why are these problems getting so complicated? Because they're AP style, aren't they? All right, so there's our derivative of f of x. And we know that if we plug in 0, we will get f prime of 0. Guys, if you remember, this is like the pot-SOT, the point of tangency and the slope of the tangent. This guy, point of tangency, this, slope of tangent line. Slope of tangent. Okay, we plug in 0. We get 0 minus 1/2 minus 3 sine of 0. Sine of 0 is 0. So f prime of 0 equals 1/2. Okay, that simplified pretty nicely. If you were allowed to use a calculator on this problem, which, I mean, we were at the beginning because we had to figure out what a was, you could plug in f prime of y1, right? You could do math 8 with y1 and plug in 0 for x. We haven't done that in a while. I'm going to do that. Math 8 gets us a derivative. We want to plug in y1 as our function because we already plugged that in there. y1, and then x equals 0. And we get negative 0.5, which is negative half. Woo! Oh, that minus. Whoops. Totally messed it up anyway. All right. It does not tell us that it needs to be in slope-intercept form, so we're going to write point-slope form, which is y minus equals parentheses x minus. Our slope is negative 1/2. Our x value is 0, and our y value is 3 from our point of tangency. If you want to simplify that out, you absolutely can. Y minus 3 equals negative 1/2 x. And then add 3 to both sides. Y equals negative 1/2 x plus 3. Oh my gosh, looky right there. This is your y-intercept. What the heck? And that was the y-intercept of that line L. Negative 1/2 is a reasonable slope for this. If I got a positive 1/2 and I looked at this graph and I'm like, that's a negative slope, that would be a clue that I did something wrong. Okay, let's keep going. At what ordered pair other than 0, 3 does the graph of line L intersect with the graph of f of x? At what ordered pair other than 0, 3 do those two functions intersect with each other? We're looking for this spot over here. What is this point? We know this is 0, 3. This one we don't know. That's what we're looking for. Well, now that we know what this line function is, we just have to figure out, like, set it equal to this function right here. Okay. That sounds a lot to me. Like, we're going to plug this into our calculator. We've got y1 equals our first function, that f of x. And let's say that y2 is going to be that line that we just had, negative 1/2 x plus 3. I'm going to go back to my y equals. And in y2, I'm going to plug in negative 1/2 x plus 3. And we're going to graph. We can see the original point of intersection, and then this is the point we're looking for. And again, I have not actually done it on this type of a graph. I'm sorry. I've done it all on the normal graphing calculators. We're going to hit second and then trace to get to the calc menu. We're looking for an intersect, which is number 5. It's a 5 on the normal calculator. Makes me feel better. We are looking for the left bound and the right bound. So we are currently slightly to the left of that point of intersection. So I'm going to hit enter. And I'm going to kind of scoot my finger over. If you're on a regular graphing calculator, you'll hit the right arrow key. We're on the right bound, hit enter. And then there is a point of intersection at 3.3897, 1.305, etc. So The point is 3.390. And then the y value 1.305. Cool. X value, y value of that point of intersection. Last thing we're going to do on this page, find the area of region S. Area of region S. So region S is this little guy right here. It is bounded by two functions. It's bounded by our y2 function, that line, and it's bounded by f of x, which is our y1. It looks like the line is above the f of x function. So this guy is going to be our blue. The line is blue, and the curve is the pink. It's beautiful tracing. Okay, we want to find the area between. To find the area between two curves, you're going to take an integral of the top curve minus the bottom curve. And the A and the B are the points of intersection. We know this point of intersection is 0, 3, and we now know this point of intersection is 3.390, 1.305. And of course, A and B are the x values of those points. So this point we learned was 3.390, comma 1.305. This is B. Awesome. So down here, find the area of region S. This is going to be the integral from 0 to 3.390 of the blue, which was the line, and that line is negative 1/2 x plus 3, minus, I'm just going to put f of x because I don't want to write all that out, and neither do you. I imagine. I mean, if you really want to, go for it. Cool. This guy was y2. This guy was y1. So what you're going to do in your calculator is you're going to do the integral. Which is math 9. The integral. The bottom is 0. The top is 3.390. Okay, one of the reasons it's important to go to 3 decimal places is if we make that the standard, then you should get the same exact answer that I did. If we did not go to 3 decimal places, it would be oh so slightly different. Okay, in here, blue minus pink. This one right here was y2. So vars, y vars, number 2, minus y1, vars, y vars, pick number 1. And it's dx. Enter. 6.982. Okay, you do not always have to do all of your integrals by hand if you're allowed to use a calculator. Like, I know that we can take the integral, the antiderivative of both of those, and plug those in, but like, why? Okay, use a calculator when you're allowed to, unless you need just like some practice. All right, we got one more page of this stuff. The same type of problem. You might want to try it on your own first, at least to get started. Let's see if we can figure out which function is which. Okay, pictured to the right are regions R and S, which are formed by the graphs of f of x and g of x. F is 1/4 plus the sine of pi x, and g of x is 4 to the negative x. So this guy right here is a decreasing exponential function. So that's definitely going to be this guy. This one has a sine, so it's going to be the curvy curve, the one that kind of looks like a parabola, but it's not. I'm going to label these f of x, g of x. And I'm going to be even more specific. G of x is this curve. Over here for R, g of x is the top part of this curve. even though it's the bottom part over here. And then this again is g of x. So after your points of intersection, g of x and f of x flip-flop which one is on top and which one's on the bottom. So it's important to label every single section, especially when you're doing a test, because we forget to do things when we're taking a test. All right. Okay. So I've got all of my F's and G's labeled. We want to first identify points of intersection of f of x and g of x. You would not be asked to do that by hand when the problems are this ugly. I mean, okay, they're lovely in their own way, but points of intersection. So we're going to plug this guy in. Let's do f of x as y1 and g of x as y2, just so that we can be consistent. I'm going to go on in, erase all that I've got. 1/4 plus the sine of pi x and below 4 to the negative x. Let's graph these guys. Ew. Okay, we are just looking at a very, very small region of this graph. So I'm going to change my window a little bit so I'm not focused on all of it. I want to make this way, way smaller. I'm going to make my x min be 0 and my x max be 3. I don't know. Let's try it. And then y min can also be 0 because none of this stuff goes below the x-axis. And then y max, I don't know, 10 seems fine. I don't know how high. Oh, no, it wasn't that high on the graph. So how about 5? Let's graph it again. Nope, I need more. Make that lower to like 1.6. Y max 1.6. And then make this 1.5. Oops, window. X max 1.5. Hey, that looks pretty similar. Mine's maybe a little bit more stretched out than this one is, but it's fine. It gets the job done. Okay, so we've got R over here, and we've got S in between over here, and then this area we don't care about. Okay, so we are looking for this point of intersection and then this point of intersection. I'll hit window one more time so you can copy that down if you want. Okay, second trace. We are looking for points of intersection, which is number 5. You can just hit 5 or you can go down to intersect. Okay, left bound. We want to be to the left of the point. So there, you probably have to hit the left arrow if you're on a normal calculator. Enter. Just trace a little bit to the right, hit enter, and it finds your point of intersection that is between. So this point, that point is 0.178, comma 0.781. It's kind of fancy. And then the second one, you're going to do the same thing, and you're just going to do it for the other spot, and it's 1.25. 1, comma 0.25 is this point. And this was 0.178, 0.781. Okay, labeling it on our graphs helps us find those numbers later. The thing we especially need for that and that point is the x value, because that's going to be like our A and B if we find S. And this point, the x value will be B if we're trying to find R. Okay, find the area of region R. Area of region R is an integral. Integral from 0 to A. It looks like when I did this last year, I got a little bit lazy. I'm going to show you how we can be lazy. A is this number, right? The x value there. So let's say that this is A, and then this number is B. Now that we've labeled A and B, I can use the letter A anytime I want to say 0.178. Okay, looking back at that graph, the left end is x equals 0. The right end of R, that intersection point, is the 0.178, which was here. All right, we need our top function minus our bottom function. Think about which function is above which function for R. G of x is above f of x, so I'm going to put g of x on top. G of x is here, and then f of x is here. Do not put y1s and y2s into this. Do not write your calculator steps like Math 8 and all of that when you're actually doing a test. The graders do not actually grade that. They don't see y1 and y2 and think that's okay in here. Okay, so this is g of x minus f of x. We need our functions to be in y equals. That way we don't have to type them in more than once. They were already typed in. Mrs. Campbell, 4 to the negative x. Okay, we said y1 was the first one, and that was f of x. So you can make a note to yourself, but that's it. This is y1, this is y2. So let's take that integral, Math 9, from 0 to 0.178 of, and then we're doing y2 minus y1, which is the same thing we did here, just our x values have changed, and then our actual functions from the inside have changed. Bars, y bars, 2 minus bars, y bars, 1. 0.065. You might be thinking that looks like a really small number, and it kind of is. Think about how small our window is. This height is like 1.5, and this was like 1.5 across or something like that. Okay, next one, find the area of region S. So same deal, except we have to change our integration limits, like the A and the B. Okay, so for S, the very far left is the 0.178, and the far right is 1. So this goes from A to B, or you could say it goes from 1 to 0.71. Wait, where'd it go? I can't even read my own handwriting right now. A equals 0.178, B equals 1. I don't know, man. Okay, for S, f of x was on top. So f of x is going to go first, right? You have to subtract big minus small in order to get that positive area. The second one's going to be g of x. So it's always top minus bottom. We have different A's and B's this time, like top and bottom. Otherwise, we're doing the exact same thing, Math 9. So this is 0.178, if I can read properly, and this is a 1. This is y1 minus y2 this time, minus y2, and it is 0.410. Okay, so the big differences here, the limits of integration changed, and then the y2 and the y1 swapped depending on which one was above the other. All right, we got one last problem. Find the area of the unshaded region bounded by the graphs of f, g, and the x-axis. This is weird. Okay, the unshaded region bounded by f, g, and the x-axis. So f of x is here, g of x is here, and then this is f of x again. We want to find that area, that whole area down there that is white. Okay, so what we're going to do is we're going to start here, and we're going to go as far as we can where we have the same top. The top is f of x until we get to straight down this x value. So from 0 to 0.178, our function is f of x, and we are finding literally just that one integral. I'm going to do this up here instead of down below. So we're going to find the integral from 0 to 0.178 of f of x dx. Then we're going to add to that the integral where g of x is the top function. G of x is the top function from 0.178 until we get to here, and that point is where x equals 1. So plus the integral from 0.178, like where this one left off, to 1 of g of x dx. And then we have one more tiny little area. Gray. So that other tiny little area is over here. F of x is this function again, right? We swap f and then g and then f. So plus the integral from 1 to, oh, we have to figure out where that touches the x-axis again, of f of x dx. Okay, so we have to find a 0 of f of x. Where does f of x hit the x-axis? We've done enough of those. The 0 is 1.08. There you go. Okay, so you're literally going to type all that into your calculator, and it's going to give you a number. Our number is 0.486. All of those together. So put it in one big string so you don't have to add up a bunch of decimals. Okay. Anything else? F of x equals 0 to c of f of x dx minus. Okay, there is a different way that we could have done that one. Instead of looking at all the tiny little pieces, the other way to do that last problem is to realize that the white area is the area that is underneath F and underneath G. I'm going to draw that again down here. Okay, so here was S. Here's the function F, that top function, and here's the function G, and here's the x-axis and the y-axis. If you take the function f and you find that area from 0 to 1.08, and then you subtract out the area of s, you're going to get this area, right? So the integral from 0 to 1.08 of, was it 1.080? Yeah, sorry, it was 1.080, 3 decimal places, Mrs. Campbell. Consistency, 1.080. So it's going to be f of x minus dx minus the area of s, right? Minus area of s. So that integral also gives you 0.486. Awesome. Yay. Okay, the ways that I was finding like what function was above is I looked at the points of intersection, went straight down, and then I figured out like what was the x value where we touched the axis, and that's our limits of integration from there to there, there to there, and there to there. So it's always straight up and down, never diagonal. All right, guys, that's it for that video. Have a good day.